speakers and things that I showed this to you and never told you what it was, before class. It was more for fun anyway. So the professor before me did it for his class. He teaches the physics of audio and video. And so it was a nice way for him to start his class. And I thought it was fun, and it was already set up, so I thought I'd let you enjoy it. And then he did this song again today. Basically, these are Lissajous patterns. Lissajous, that's a guy's last name. When they redid this, I had them, there's a switch, so I can plug something in back there in the projection booth, and it makes a laser point up there. And I've aimed the laser at two mirrors. They're attached to two different speakers. And so this cable goes back and sends the sound to those speakers in addition to the big ones so you can hear it. And it makes them vibrate in and out. So the mirror moves. Actually, they kind of hinge like this. So the mirror's going. And it deflects where the beam's at. Well, one speaker's like this, and the other speaker's up here going like this. So you can get two perpendicular directions of motion. And so anytime there's a certain frequency, vibration, it makes it wiggle in one direction and or the other. And you can get these patterns, which looks fun, and matching the music. We will cover waves and sound and oscillations this semester, but it's later. But he's already on it. So actually, his whole class is on it. So I did it while we could. So, questions or concerns of things since Monday? Things you've been wondering? Had a few of you communicate to me through email. Things I've learned from some of them in case others of you have questions. It appears through your Turning Point account, Turning Technologies account, the student store through the university where there's a little discount. They give you some options, some packages and whatnot. There's even more options from the Turning Technologies website themselves. For example, we got to check this, but if you just want to buy a license and a license only because you already have a clicker or you don't want a clicker, you might have to go there. And somebody said it was like 20 bucks as opposed to the 70 bucks where you have to, I think is where they package it with a new, most recent clicker. So you can buy it in 1, 2, 3, 4-year options. I repeat, so others in the video. And it starts at 20, and then 30, and then 40 or 50. An option of buying a multi-year license is because if you plan to be at the university a while and you anticipate other courses that might use this because it's the university standard and there's a fair amount that do, but not everybody, then it's a little cheaper than having to buy it every year. But good, and thank you for that information. I can see many of you have already registered a device. Some have registered but don't have a license yet, but we're getting there. I'll ask some questions in a week, next Wednesday, and we'll try it out. Or maybe I'll try it Friday, just for those of you that have it, to see if it's working, but it won't count for points. While I was babbling there about clickers, you think of any questions? All right. How many have had a chance to read the syllabus? Hey, okay, that was more than half. How many have started your homework on it and your homework on chapter 1 and 2? A little less of you, but there you go. When's it due? Sunday night. They're both due, so you guys know that. Again, on WebAssign, refer you to the resources section where I've uploaded some files, hence the syllabus. But there's a calendar saying what we're doing each day and when due dates are and exams. And the final exam, which we can't adjust. The superhero paper stuff, that's all on there. I did meet our TA, our teaching assistant. Oh man, he's the nicest guy, very respectful. Mohammed's his name. I posted that. He's going to get back to me with his office hours so you can have him as an additional resource. He's just rearranging his classes too. He's a graduate student here, brand new. And so once he figures out what his schedule is, he'll tell us how he can help us. All righty. We started talking about science in chapter 1, scientific method. mentioned a few other things. Here's one, scientific attitude. So you know, I say in the syllabus, and I tell you, I use this a lot. We're parallel. I'm not one of those where I'm going to teach you a bunch of different stuff and this a whole bunch of other different stuff. We work well together. It's not like you have two different things to worry about. However, I will mention some things that he doesn't and vice versa, because we don't cover everything. But I go through it, and so if you I strongly suggest you read all this, and you will get more out of this class too if you have a chance to look this over. Not understand it, but look it over before we discuss it in class. Hence the pre-lecture questions that I'll start next week. All right, scientific attitude. See, it's right here. I'm looking at it. I got definitions from him so we don't contradict. The main thing about science is it rests more on an attitude than it does on procedure or certain particular methods. And as he mentions, and I agree, there's three things we expect scientists to adhere by. Inquiry is one. And that kind of goes with the scientific method and people being curious. It's just, you got to inquire and check things out. That's kind of the difference between, as I mentioned, a normal person and a scientist. Do I mean that scientists aren't normal? Well, a lot of them, yeah. Integrity is another one pointed out. Integrity. It doesn't do any good if you can't trust the scientists. They're trying to figure things out so that others can learn and explain how the world around us works and that we can depend on it. Well, if they're fudging their data or lying or just trying to make themselves look good, it becomes apparent real fast because others try to do it and realize, liar, you're wrong. So you got to have integrity to be a scientist. Those that don't get shunned out real fast. And probably the hardest one, because it's hard for everybody, right, to be humble. Humility. If you mess up, you got to admit it. Again, it goes back with integrity. If you made a mistake, you need to let people know, or we can't rely on it. And I'll just apologize right now. I'm human. I'm sure there'll be a time during this semester where I mess up, and in my mind, big or something. And I'll, dang it! Now I've just confused them. If and when I catch it, and you can tell me, I can take it. I'll tell you about it. I'll admit it because I don't want you to be confused. So yeah, it's about an attitude. A lot of that goes with science that I don't think a lot of people realize. Oh, there's just these robots that are all about facts. Well, if you can't trust the facts, then it's useless. So what is a fact? If you were to go home and tell your roommate or your younger brother or your mom, I'll probably mention this a lot. I said about the paper, you learn things better, or you can gain a lot about learning something when you try to explain it to someone else. You guys are here, and unfortunately, most of lecture is you sitting there listening, trying to take in what I'm saying. And you can gain a lot that way. But when you try to regurgitate it back out, that's when you can find your holes. Like when you try to say it. Oh, yeah, I got it. And then oh, what do you call that? Was it velocity or acceleration? Darn. And that's where you figure out where you need a little more help. And you'll grow from that. And it'll make more sense. So if you were to explain what a fact is, what would you say right now? Something that's proven. No need to debate it. Good. Good. Ah, that's true. In the layman's world, a fact is permanent, definite, non-changing. In the science world, you're correct. Facts have changed. Can you think of an example? That's one I was going to use. Have you read the book? It's the one he uses. Yeah, they said the world is flat. That was a fact. Let me read the book's definition. It says, a fact is a close agreement by competent observers, I love how he throws in competent, of a series of observations of the same phenomena. Okay, raise your hand if that sounded like this. Bunch of big words thrown together. So let's break it down. That's what definitions do. They try to get it all concise. So we observe a bunch of stuff going on. And if I think that's what's going on, and I watch it again and again and again, okay, this is what I think is going on. You observe them, and that's what you think is going on, and that's what you think is going on. We've all observed it, and we're in close agreement. Then we can call that a fact. And they thought the world was flat. They were wrong. They gained more information, they made additional observations, and eventually they realized they were wrong. They admitted it, and when they made a new fact, the world is round. And people were in close agreement with that based on their series of observations. So facts can change. But we rely on them until we know otherwise. Otherwise, we can't rely on anything, and we can't try to predict or say anything. So we do go with them. Now, that means you can trust them as well as we know at this point. So, all right, there's something else in science. A law or a principle. In my mind, they're the same thing. What's that, or how's it different than a fact? Your easy answer is, well, they're in your book. You can just look it up. But what do you think? You've probably heard of some laws. We're going to get into Newton's laws. There's Newton's first law, second law, third. The laws of thermodynamics we're going to get into. Yeah. That's good. Do you read the book? See? That's right. It's a statement or a hypothesis, kind of a general hypothesis. How's he word it? About the relationship of natural quantities that's been tested over and over again and hasn't been contradicted. So it's not a fact. This is just that the world's round. That's not a law. We can't use that law to do other things. We can use it to understand things, sure. But it's not like a hypothesis. It's not helping us make an educated guess about something or a general statement. That's where the law comes in. It kind of helps explain relationships. For me, that's kind of the key word. It will explain, well, a hypothesis or statement about relationships, how things relate to each other, so that we can guide it. For example, we're not there yet. It's 3 chapters later. But Newton's second law, you might not know what it is, but raise your hand if you've already seen this sometime in your life. Raise them high. I want to see. Yeah. In my mind, that sums up Newton's second law. We'll get there. It's force equals mass times acceleration. That's a law because it shows relationships between these variables. If you increase the acceleration, it requires more force. If something's bigger, it'll take more force. There's a relationship there. That's a law. And in that case, that's Newton's second law. All right, what else do we got? We got theories. What's a theory then? I got to stop touching my black pants. Oh, well. A theory. This one's probably even more than the other 3 because we use that more in layman's terms. And here we're using it in science terms. And is there a difference? Yeah.
Well, in science, theory is usually a widely accepted explanation for a phenomenon, whereas in layman's terms, usually people talk about a theory like, oh, well, he has this theory about what happened, and it's not necessarily accepted.
I like that. Yeah, in layman's terms, somebody just has a theory on something, and you just kind of naturally already assume that, well, I don't know if I can trust him. It may or may not be true. Yes? Yes. We're defining theory now. Let's finish that, and then we'll make the difference. it'll be more obvious. Well, what's a hypothesis? We can define that one. An educated guess, a prediction. So that's predicting something, what you think will happen based on what you already know. How do you get that theory, prediction, that hypothesis? What do you base it on? What you already know. You base it on facts and laws and theories. These can help you make those predictions because you know this, and this law defines this. So given this, I would predict that if you have something that's bigger, it'll be harder to push in general. A theory, you also said, I think that was similar words to the way the book defined it. Synthesis of a large body of information that encompasses well-tested and verified hypotheses about the natural world. So yeah, a theory involves laws and principles and facts. It kind of like takes them all together. It's the big picture. You've probably heard of the theory of special relativity? Einstein relativity? Really? Only that few? Well, good. We're going to cover that one too, right after we finish all this motion stuff. And the theory of general relativity is another one. See, I pre-thought of these ahead of time but didn't write them down. String theory, you've probably heard of that. So these are big. It involves many laws and principles of well-tested things. But again, they can change. As we learn and gain other laws and other facts, we adjust theories. So they can change. We have integrity and humility. We'll admit when we learn something new and adjust it. But that'll help us make predictions and make hypotheses to understand what's going to happen around us, or so that we can understand what's going on, why it did perform the way it did. Does that make sense between these three? That's mainly what I hope you learn out of this first chapter. Those will probably be on the test. They're probably they're in your homework. So in science, remember I said it's one way of gaining knowledge about the world. It's more important in science, we say it's science, if you can test it. You have to be able to test it. If you can't test it, if there's no way of proving it wrong, then they generally don't call it science. For example, the world is round. Can we test that? You're not sure. All right, think about it. Can we test? I'm going to make a prediction, a hypothesis. The world is round. I think the world's round. We already know it's a fact, but you know. Okay, now we need to do an experiment. Are there experiments we could do to prove that? Yay or nay? All right, how many are just unsure versus how many just don't want to give an answer? I'm confused here. This is where I need interaction feedback to help you. Yay. Yay, we got a yay. Do you mind sharing maybe an idea how? There we go. Let's go out in space and look at it. We can do that now. Poor Columbus. He couldn't. Yeah. Even if you can't think of an experiment, you should realize somebody must have already come up with lots of experiments because we call it a fact. So we proved it. Yes. Give me an example of something we couldn't prove. Giving everybody a chance to think. Does God exist? Yeah. In our current state, can we prove that? I'm not going to get into it here, but through science, right now, no. You can't. Scientists, that's where there's a lot of beef. Whether God exists or not, there's other ways that people feel they can prove that. Science is not one of them. We can't devise an experiment to test that, to say that he doesn't. So we couldn't say that's a scientific statement, that God exists in the realm of science. That's the biggest beef between evolution, Darwinism, and science. They wanted teachers to share equal time with their theory. They have theories. Theory of evolution. So that they're not biased. the problem most scientists had was, well, this is my personal vendetta, but I think they were a little lacking in some of these. Some of them, they just didn't like it. But the true scientists didn't like it because they just didn't want them to call it science. I'm all for the theory of evolution, but it shouldn't be taught in science classes because that's not what science is about, because we can't disprove it yet. They've detected facts and things that seem to make it true. But it's more important that you be able to disprove it to call it science. That's a good example of one where people have been saying, but there's this, and there's this, and there's this. Yeah, we can prove that that's true, and that's true, and that's true, but we haven't fully encompassed that it's not true. Thus, it shouldn't be a scientific statement. And so, yeah, it can be taught. They just don't want it taught in science classes, was the big beef about all that. Questions, concerns about what science is? Probably have it down by now, right? All right. Chapter 1, then, or 2, on Newton's first law. You know, I never asked, how many of you had a physics class, a physical science class that you remember, in pre-college, high school? That looked like over half. All right. I'm guessing if you had it, you probably covered forces in motion, and maybe heard of Newton. So hopefully some of this will be familiar. Well, Galileo was concerned more with how things move than why they move. We'll get to the why in chapter 4. Back with this. But right now, we're just going to talk about how things move. We're going to make observations of the world around us, define some relationships, and make a law. Galileo rolled balls up and down inclines. I'll probably be doing that later, not today. But the first thing he discovered was that if you roll a ball down, it goes, and when it hits the bottom, the flat part, it keeps rolling. Does it stop? Eventually, yeah. We're used to seeing things stop. So this law might seem obvious to us now, but then they didn't have this law and the terms we're going to define. Everything seemed to eventually stop. You throw something up, it comes back down and stops. You slide something, it stops. You're in a car, you let off the accelerator, you eventually come to a stop, right? So what was amazing was that he started rolling things and changing the angle, and whether it went back up, he's like, keep rolling, and it'd go down and back up, and down and back up. Well, he gradually just made this a little lower. Well, now it'll go down, and it comes back up to the same height, but it took longer to get up there. Maybe here, and back. Well, what if you make it flat? The idea was he'd roll it, it'd go down, and it's trying to get back up to that height. Because it did in every other case that he did. So if the ramp doesn't come up, the ball should just keep going on forever. This was his reasoning that got him to think about this first concept called inertia. Inertia. That's how I sum up Newton's first law. We'll define it here in a moment, but let's define inertia. Who's heard of it? Most of you. How would you define it? It is a property of matter. You watch Bill Nye? I did too. Bill. Inertia, it's a property of matter. That's all my wife gets out. Yeah. Well, she knows more now because she has to listen to me. But yeah, it's a property of matter. And that's true. All matter has inertia. Let's add to that, though. Okay, it's a property, but that doesn't really tell us what it is. Yeah, Brenda. That's how I define it. It's resist a change in motion. The book defines it as sluggishness or apparent resistance of an object to change its state of motion. Okay, what's that mean? You've heard this, I'm sure. An object at rest wants to stay at rest. An object in motion wants to stay in motion. unless acted upon by a force, which we'll get to. So it's happy. This is its state of motion, rest. So if you try to change that, it'll resist you. And that's why it stays at rest. Things at rest want to stay at rest. Things in motion will want to stay in motion. But if something acts on it, it could change that motion. It'll resist it, though. So it'll require a force. Before I show you a demonstration, I want you to realize inertia is not the reason things don't move. It's this property of matter. But don't think of inertia as a force. You know, you're happy sitting there, so if I try to walk up to you and push you, you're at rest. You want to stay at rest. So her inertia is going to resist. I'm not going to. Your eyes are too wide. I'll put you at ease. When I push you, though, your inertia will try to resist changing your state of motion. You're happy at rest. You want to stay that way. So if I'm trying to change that, you're going to resist it. That's not a force you pushing back on me to resist. It's just a property. So don't think of it as the reason or the force, or you might get into trouble with some of these questions and reading the text. Let's do a demonstration for it. Who's ever tried to pull a tablecloth out from underneath stuff? Raise your hand. Anybody tried that? Nobody? You gotta higher up. Okay, I see about 4. I thought there'd be more. All right, of those that tried, were you successful? No. Okay, raise your hand if you've always wanted to try, but you never did because you were afraid of breaking something. More of you. Okay, well, today's your lucky day. Keep your hands up. Who wants to do it? Who really wants to try it? Want to try it? Yeah. Come on down. Don't worry, I'll give you some pointers. I'll give the whole class pointers before I make you do it. So hopefully you'll be a little more successful. But it's okay. If you break this, I can go back to the thrift store and buy another one. This is ceramic. So yes, it's breakable. This is glass. It's breakable. So the idea is these are at rest and they want to stay at rest. So if you pull on it, they're trying to stay at rest. And the friction between the tablecloth and the plate, grab it, push on the plate, and try to change its state of motion. So if we can yank it fast enough, its inertia, that property of matter, will kind of keep it put. And if the tablecloth's out from underneath it before it wants to start moving much, we won't pull it off the table. You can see if you pull slowly, it doesn't work. So the first tip is to pull fast, as fast as you can. And to help with that, a lot of people will start like this and just start pulling. Well, as soon as you start pulling, look, it goes slowly until you get up to speed. We haven't got to acceleration yet, but you've all heard of acceleration. That's where you increase your speed. Well, let's accelerate and get up to speed before. If you step back just a little so they can see, just right here. If you pull like this, by the time the tablecloth's tight and it starts pulling on the plate, you'll be up to a higher speed. So that's my first tip for all of you that want to go home and try this. To start with a little slack and up here. Tip number 2, go down. Go down. Most people get all worked up and scared, and they know they have to go fast now, so they do this. And they go, wah! Well, if you go up, these will come up with the tablecloth. You don't want them to come up off the table. So go down, and it'll come off smoothly, hopefully. Tip number 3, cut the seam off your tablecloth. It's really annoying. If you have a seam, it's just when it goes under, it's going to get caught and put an upward force on your plate. It's really, really annoying. Okay, you go ahead and grab the tablecloth and get ready.
Are you sure you don't want to do it first?
Oh, no, you'll be just fine. I'm going to make it, add this just to scare you some more. Go ahead and wad it up a little. Don't worry, we'll help you out here. All right, you'll start up here, remember, and you're going to go as fast as you can, and you're going to go down, right? Start with your wrists up here. That way you'll be up faster. Are you ready for this? We'll give you a drum roll. Yep. Whenever you're ready. Thank you. See? You're a pro. All right, but the rest of you are good scientists, and you made observations. Tell me what you observed. Anything. The silverware moved? You heard it, didn't you? What else did you observe? Everything moved a little bit, yeah. But she went fast enough that it didn't pull it off the table first. The tablecloth was out from it. Anything else? All right, let's try to explain these two. Well, we just kind of explained that one. Let's go back to why the silverware move more than the plate and the glass? Less weight. Okay, well, why does that matter? This is that reasoning part that I'm going to hopefully try to teach you to do in this class, and we'll expect of you. Yeah. It has less inertia? How do you know it has less inertia? You're right. It was affected less. Inertia is a property of what? Matter. Did you want to add something? Oh yeah, we would like it to come out, not bunch up, and be smooth. But in theory, it should. Oh, the weight. That does contribute. We're going to learn that the weight of something does affect the amount of friction between the materials. Good thinking. Forward thinking. Friction's a later chapter, so we'll save that for later. But yes, that's true. I don't mind telling you. Yes, it is inertia. It has to do with weight. And yes, it's inertia. Inertia is a property of matter. How much mass? Mass is a measure of how much matter something is. And things with more mass, weigh more. And indeed, that's the reason why they have more inertia. So even though I was scaring you, this actually added mass, added inertia, which means it has even more resistance to wanting to change its state of motion. And these were less likely to be influenced by the frictional force than these that have less mass, less resistance to change, less inertia. So they were affected more because they have less mass. Does that make sense? All right, let's try it again. Because it's fun. All right, help me out. Set them down, though, before I accidentally knock them off. All right, let's do it a different way. Show you a few other ways you could have fun with this. Here's a piece of paper and an aluminum rod with flat ends. I can set it there. And same idea. If I could pull that out fast enough, the rod's inertia, because of its mass, should resist wanting to change and not fall over. So you try to yank on it, and it falls. Anybody think they can do it? I'll tell you, it's possible. It's not a trick. Anybody want to try? I'm big on demos and volunteers, so if you want to have fun this class, come on down. Nobody? Well, then I can't tell you the secret. All right. I guess I could make this $1 bill, and if you're able to pull it out without this toppling, you could have it. Oh, what the hey. If I have one, let me see. I do. All right. See? No, it's fine. Go right ahead. He's good. I won't lie. Most people usually mess up a couple times first. So kudos to you. You went for it. They usually kind of wuss out. For those of you that find it's not possible, do what we did with the excuse me, the tablecloth. Start with a little slack and get it going fast and down, right? You just kind of, piece of cake. Another fun one I debated whether to do, say you had like 2 wine bottles, I mean sparkling grape juice bottles, and you could flip it upside down on top of each other and put the dollar bill there. Try to pull it out before. You know, party tricks, party tricks. There's one. Put this card on here. There's a flat part of this ball. I'll set it right over the cup. And the idea is if I fling it quickly enough, it vibrates. It'll come right out. The inertia, due to the mass of the ball, resists changing its state of motion. It's at rest. It's happy. So this slides right out, and then gravity just pulls it down into the cup. You could do this with a quarter or something if you want, if you get good at balancing. Let's try it out here. Let's see, if I balance it on my finger above the card, I haven't done this in a while, and then you try to flick the card. Woo! Because of inertia. Things at rest want to stay at rest. What? You don't believe me? Let's just move this up here. All right, practical application here. You're like, yeah, this is real good, Adam, but give us. All right, forgive the crudeness, but you know, you're on the John. I'm sure this has happened to all of you. You have toilet paper rolls. They're in different states. They start out nice and big, and at some point they get small. And invariably, what annoys you when you go to pull to rip a section of toilet paper off? It keeps rolling. Which one of these is more likely to do that? This is the reasoning part. You can just guess and make a hypothesis based on what you know. Or let's start applying some facts and observations of, in theory, what we just talked about to this. Yeah? There's less mass. So it would resist you less and thus come off. Okay, anybody want to add to that? That sounds good. It's logical. Then let's go for it. I'll attempt to yank them the same. Here, let's start with a little. I start with the big one. Oh, that's good. Yep, that ripped. This one? Do you see? It ripped, but it kept coming. So if I did a little less yank, but it's annoying to clean up. So. As opposed to this one, piece of cake. Yeah, this works in rotation too. We're not going to cover circular motion much in this course, but everything I'm teaching you about laws of motion and whatnot work if you're going in a circle too. So this inertia thing works in a circle. They just call it rotational inertia. And this one does. It has more mass and how it's distributed, so it resists you more. Thus, you can break it easily. Where this one's annoying. And I'll have to do this later behind class. So see, physics is practical. All right. Next time you're going to the bathroom, you'll remember, right? So Newton's first law, we've already defined it. The book defines it as every object continues in a state of rest or of uniform speed in a straight line. That means in motion. Unless acted on by a non-zero net force. He has to get all these fancy words in there that'll make sense as we finish explaining it. But things at rest want to stay at rest. Things in motion want to stay in motion. They actually will stay in motion. They'll just keep doing what they're doing because they don't want to change their motion. So if it's going 50 miles an hour, it'll stay 55 miles an hour in a perfectly straight line until something tries to influence it. That's on my bucket list. I don't have a long bucket list, but I would like to be able to go out in space and just chuck something. Because what will it do? Yeah, the speed I got it up to, it'll just maintain that speed in a straight line until something, a force, causes it to change that motion. Bend, curve, slow down, speed up, whatever. Burn up in an atmosphere. But that would be cool. Just so, wait, am I ready for that part? No. Let's do it anyway. We'll come back to it. So why does this stop? Why do we see things stop? Yeah, see, you know friction. Friction's a force, and it's acting on this object to slow it down. Slowing down is changing motion. So this is a hover puck. I'll try to minimize friction. It blows air out the bottom to try to get rid of friction. Now, if I push it, things in motion want to stay in motion at a constant speed until something, the plate, exerts a force on it and changed its motion. So if we can eliminate friction, which we deal with a lot in this world, Galileo was right. His observations were right, and we have Newton's first law. It's called a hover puck. Bought it as a toy. Paper, force. If I have it going slowly, it stays slowly. If I have it going faster, it stays faster until a force. Or the battery dies. All right. So a force, we've kind of already defined. Force is important. It's an interaction between two things. That's how I like to just sum it up. An interaction between two things. Your book, as defined in your book, it's any influence that tends to accelerate an object. You can see that already. In order to accelerate this mass, an object that has inertia, remember mass is a measure, inertia is a property of matter. If you want to accelerate it, you gotta push on it or pull on it. Influence it somehow to change its motion. A change in motion is acceleration. Note that. Things at rest want to stay at rest. Zero velocity, zero speed. Things in motion, 55 miles an hour, let's say. It doesn't change its velocity or speed unless it accelerates, speed up or slow down, and it takes a force to do that. So that's any influence. But it requires two bodies. It's an interaction between at least two things. You guys okay? Questions? Okay, well, you can have more than one force on something. So we define net force. I like to write it as F sub net. Let me just show you an example. Our textbook author, you'll probably read about this in there. He was a painter, and he did a lot of hanging on planks on the sides of buildings to paint. And he would stand on here to paint when he needed to paint. And he had a buddy that taught him a lot of this stuff that he gives credit to, got him interested in physics, and he became a physics teacher after he was a painter. So you're on this plank. Well, why is the plank not well, let's back up. You guys can probably already think of, what are some forces going on here? Gravity. So you guys already know about that. What's it acting on? Which object? Everything. Yeah, so if acting on this person, we draw a dot on his center of mass. You know, it's acting on all of him, but we pretend like if all of his mass was concentrated at one point, it's center of mass. We'll put it here. There's a force down. We'll call that, be consistent here. 1. There's 1 on this one. Let's say he's bigger. Then the arrow will be longer. Force is a vector. A vector. As opposed to a scalar. We're going to use different things, and I'll tell you what they are as we go along. If I forget, just ask. But a force is a vector. Something that's a scalar is like mass. Mass is a scalar. Anybody already know the difference? Because you've heard these before? Yeah, that's the bottom line. Vector adds direction. So mass is like, I'm about, I don't remember anymore, in kilograms. Well, whatever. I weigh about, no, forget that one. 30 kilograms. Let's just say that. That's mass. That's a scalar, just the amount, the magnitude. It doesn't matter which way I'm pointing. Force, though, it matters which way the force is acting, in this case down. So we draw a vector arrow, and the length represents the magnitude, and obviously the arrow, the direction. So you can see already that this magnitude is larger. So this is a bigger force than that one. We're going to do this all semester. These are called force body diagrams. Force body diagrams. Fancy physics term for draw a picture of what's going on. It really helps, especially when you're not sure how to set the problem up. Just start writing down the facts and the things you know and the laws that we've given you and relate some relationships and draw a picture, and piece by piece it can come together then. All right, we also have a force acting on the plank. We'll put it in the middle. All right, there's 3 forces acting down, so why doesn't it fall down? Yeah, the ropes are changed. There's tension in here. It's pulling up with a force. And this one's pulling up with a force. So there we go, that works. That's our force body diagram. There's 5 forces there. What's the net force? All of them together, what's happening? Is it going? 0, you're right. The net force in this case is 0. You know that because it's not moving. That's called equilibrium. Equilibrium is a state of no change. They're at rest. They're not moving. So you know they all have to add up to 0 somehow. How would you do that? You could just sum up all the forces. This is a Greek term sigma that means summation. We're just going to add all the forces. All right, we got 2 going up. So let's add F4 to F5. Because those are the forces pulling it up. Well, minus F1, F2, and F3. Why minus? Because they're down, opposite direction. If we're going to make up positive, then down has to be negative because force is a vector. Or just think of it. One's going one way, so you've got to subtract the others. You can probably see that these, the sum of those is going to add up to the sum of these because they cancel to 0. It's not moving. What if we hooked it up to a winch or something and increased F4? We made F4 larger. What would happen? It'd start moving up because this sum would be bigger than that. This would no longer be 0. There'd be a net force accelerating, changing its motion, and it'd start accelerating upward. Yeah. It would no longer be in equilibrium. You just changed its state. So that's about net force. We'll do lots of that. And that's a good stopping point unless there's any last-minute questions. All right. Thanks, everybody.